Let's take a look at another differential rate law problem, number 2 on page 6 of your homework packet. So again, we have an equation, and here we have a box with some information. And essentially, we did this experiment 3 different times and then measured the rate of appearance of the product NOBR. And here is what we found. Let's take a look and try to figure out the rate law for this in the order of these things. Does the NO affect the reaction rate? Does the concentration of Br2 affect the reaction rate, and by how much? So this one, it looks like this is constant here in 1 and 2. This doubles, NO doubles, in 9.6 times 10 to the negative to 3.8 times 10 to the negative first. That looks like it quadruples. It goes up by a factor of 4. So if something doubles and something goes up by a factor of 4, it's really doubling squared, and that squared means it would be second order in NO. So we're going to say rate equals K, and we're going to say NO squared, because when NO was doubled, essentially the rate doubled, or it went up by a factor of 4, or went up by a factor of 2 squared, and that squared thing says it's second order. Let's see, I think in 1 through 3, 1 and 3, NO stays constant. We double BR in 9.6 to 10 to the negative second to 1.9 times 10 to the negative first. That looks like a doubling effect there. So that's a 2 to the first change, and that would be a first order change for BR2. So my rate law would be rate equals K, NO squared, and then BR2. Now notice that matches up to here. That is purely a coincidence, this 2 in this matchup. It can happen, but it doesn't always happen, and a lot of times it doesn't. By coincidence, it does here. Okay, calculate the value of the rate constant for the reaction, include the units. So again, we could look at any experiment. I think I chose the one with these same numbers here, number 1, and I'm solving for K. I know the rate, I know NO, and I know BR2. So that's when I'm just taking this data and then solving for what I don't know, the K. Once I know the rate constant, unless I change the temperature, I can solve for other things. So I did this rate, I solved for K, I plugged in the values for experiment 1, and I get 1.2 times 10 to the 4. Notice messing around with units. Notice my units on K right here when it was, I just wrote my rate law. Yeah, notice my units on K. M negative 2 seconds, negative 1, which is typical of a combined third order reaction. Second order in one thing, first order in another thing. It's third order overall. This is what you'd see. Okay, I think we have a different type of question which we haven't seen. And this one says, in experiment 2, what was the concentration of NO, I think that's nitrogen oxide, or nitrogen monoxide remaining when half of the original amount of Br2 was consumed? Okay, so I'm going to look at these amounts right here, and I'm going to say, if half of this was consumed, what amount of this was remaining? I'm going to introduce something that I think we worked with excess and limiting reactant honors. And those who had honors not last year, but the year before, we probably worked with an icebox with initial change in end. We might have even applied this to equilibrium, which we're going to see a lot of in the coming weeks. But anyway, if I looked at that table, I start with 0.04 of NO, 0.02 of Br2, because I think they were talking about experiment number 2 here in the problem. And then it said we didn't have any product when we started. Okay, now it said half of the PR2 reacted. Okay, so I can say, well, what's half of 0.02? That's 0.01. And then I just look at mole ratios of this. Not at the rate law, but I look at the actual coefficients in the equation. If 0.01 of this reacts, twice as much of this might react, so I should probably put a minus sign there, minus 0.02 right here, and then it's, what is it, 2 to 1 to 2 ratio. If 0.02 of this reacts with 0.01 of this, it's going to form 0.02 of this. Okay, so that's where I got these numbers. Ultimately, I could figure I have 0.02 left of this, 0.01 left of this, 0.02 left of this. Those would all be molarities. I think I'm only asked to find the molarity of the NO, so that would be this answer right here. Okay, so this is the ice box. Okay, so we can draw a little box around it and get used to this because it's a cool way to solve problems, the ice box. Okay, now the last step here is this kind of confusing thing about reaction mechanism. So let's take another look at it. They all become a little bit different and try to find my spotlight again. And this one says, which of the following reaction mechanisms is consistent with a rate law established? Explain your choice. Well, one thing that has to happen is that, now I ended up choosing number one, but the first condition I think is actually met by both of them. That if I do like a Hess's law thing and I add up these two reactions, they should equal the thing on the bottom. So if I recognize NO is formed in one step and used up in another step, that's an intermediate. And I'll say, oh yeah, this adds up to 2NO plus Br2 forms 2NO Br. That should match up to the initial equation that we had originally. And that does clearly do that up here. Okay, so maybe I wrote that down here. I said step one, steps of number one add up to equal the overall equation. And I kind of showed that a little bit there. Tell you the truth of these questions, and almost always happens that the ones they give you show that if you're given things. But the next thing is now we got to find out, we talk about the rate determining step is the limiting reactant. So let's say number two was the one we chose. Oh, this is a slow reaction. If it was only first order in B and not any order in A, I'm sorry, in first order, this should be BR and not any order in NO, then this would be a rate law. I should actually say ER2 right there. I realize that. But how about this one? Well, the slow thing is the rate determining step, but it's got this N2O2 thing in there, and that's kind of confusing. So I look at this and say, of my rate determining step, the rate order, and again, I just take the coefficients front, is N2O2 and Br2. However, I can look at this equilibrium step here, because its arrows are going back and forth, that's equilibrium, and I can do a substitution. And I can say, oh, NO and NO combines to form N2O2, or that would be a coefficient of 2NO, so it would be NO squared, I substituted for N2O2. Now this becomes that rate law right there, which does match our overall rate law for this reaction. So I look at the rate determining step for this. Can't tell if it matches, but if I do the equilibrium substitution for N2O2, put the two NOs in this equation instead, then it does end up working. And how would I explain that? If I'm asked to come up with a reason, I would say the rate law of RDS in number one matches the overall rate law with the equilibrium substitution for N2O2. The rate of K N2O2 Br2 becomes rate of K prime NO2, and that should say Br2. I forgot the little 2 right there. So there is another example that we have.